Welcome everyone to the second session of the ICTS in-house. Our first speaker is Ashik. He'll be talking on cosmological correlators on non-Hartle-Hawking states. Over to you.
First of all, thanks everyone for coming. Today I'll be talking about cosmological correlators in non-Hartle-Hawking states. So this is work in progress with Surat and Tunir. So roughly the idea is that you see something on the sky and you want to explain it. So you can explain it using some correlation functions, and these are called cosmological correlators. I will explain it more, but this is a rough idea to start with. And the question is, what are you observing on the sky? So you know that when you go to large length scales, zoom out and look at our universe, length scales like 100 mega per second, then the universe looks pretty much homogeneous and isotropic. But this is not the end of the story. There are small fluctuations also you can observe. One example of such fluctuation is that you know that there is a constant background radiation that we see in the sky. This is called the CMB radiation. And the temperature of this radiation looks 3 Kelvin almost throughout, uniform. But there are fluctuations on top of it. Like some place it will be 300 Kelvin plus 3 Kelvin plus 300 microkelvin. So small variations are there. Now it turns out that these variations are not random. They are correlated. So fluctuations happening at one place is correlated with fluctuations happening in some other place. So this can be measured by a 2-point function, and it's a non-trivial 2-point function, so it means that there is some correlation. I'll explain this more. But now, okay, we have observed these things. Now, how to explain this? People have done this, and one idea is to use inflation, theory of inflation, to explain these fluctuations that we see today. Now, what is inflation? So, inflation predicts that, proposes that very early in the history of our universe, it went through a rapid expansion. So the universe was expanding at an exponential rate at some point in our history, and the quantum fluctuations that were present during inflation led to the fluctuations that you see in the sky today. So this is a general idea behind this cosmological correlator industry. So now simply the metric during inflation, as I said, this is a expanding universe. So you can say that the metric is roughly like this. So this e to the power 2ht factor, that's telling you that distances are expanding at an exponential rate. It also turns out that the metric can be associated with something called the de Sitter spacetime, but I won't go into that more. Now, okay, I told you that the quantum fluctuations during inflation can be mapped to what you see on the sky today. Now, what are these fluctuations? What do I mean by saying that there were some fluctuations during inflation? So assume that at the time of inflation, the universe was filled with some scalar field. For simplicity, some scalar field, and the scalar field is constant everywhere. Almost given a spatial slice, it looks constant throughout, but there are some fluctuations on top of this constant profile. And the idea is that this is inherent fluctuations in any system because these are quantum fluctuations. Now, similarly, fluctuations can be there in metric also. So earlier I wrote down a perfect metric, and that may not be true. There will be this small perturbations. Now, the idea is that if you compute these quantum mechanical fluctuations, these can be related to temperature fluctuations that you see today. And this has been done, and this arrow is very non-trivial. You have to take into account many things, but it can be done. Now, yes, this is roughly the idea. Fluctuations there evolved to fluctuations that we see today. Now, so given this idea, how can I compute these 2-point function of these fluctuations, quantum mechanical fluctuations? Now, you know that in quantum mechanics, if you want to find expectation values or of a particle doing something, then first you write down the wave function psi of x, square it, and then you can integrate it appropriate moment to get that expectation value. So this mod psi square gives you the probability that the particle is at the point x. Similarly, given a fluctuation profile, so you take a spatial slice and you say that the fluctuations were something like this, some shape, then this wave functional will give you the probability of that shape occurring. For example, this is just some machine. So given some profile of the fluctuations, the wave functional will give you the probability of occurrence of this fluctuation. So this is a rough idea, like in quantum mechanics. Now, given this, so if I have the wave functional, I can compute these quantum mechanical fluctuations. Now, how do I compute these wave functionals? So this is a simple calculation which you can do. In quantum mechanics, for a single particle, let's say it's starting at origin, x equal to 0, and evolving to some other point y. And at x, it was at 0 at some time t, which is like minus 10 seconds or something. Then it evolved to some other point y. So what is the probability of this happening? Now, this probability can be given by this path integral, where you sum over all the paths connecting these two fixed points, weighted by this e to the power is, s is the action. Now, what I will do is that you can insert a complete set of states here, energy eigenstates, and this is just the wave function of this energy eigenstate. And now I will do a simple trick. Instead of this it, I will redefine t is equal to minus I tau. So this expression becomes something like this. Now you see that if you take tau going to minus infinity, let's say that ground state had energy 0 and everything else had some positive value. So if tau goes to minus infinity, all the positive energy contributions will be suppressed, it will go to 0. So the point is that in the limit of this, you will get something which is, by doing the path integral, you will get the ground state wave function. So everything else except for n equal to 0 will vanish on the RHS. So the path integral will give you ground state wave function for the particle to be at the point y. So roughly the idea is this. So you do this path integral and sum over all the trajectories. Now you Euclideanize it, meaning that you make that change of variable and sum over all these trajectories connecting these two fixed points. Then you will get the wave function for the particle to be at y. Now this can be generalized to explain, to get the wave functional for that fluctuations that I discussed. So the idea here is that just like the fixed point y, you take a surface and put some shape for your fluctuations. Then you sum over all Euclidean geometries that have this fluctuation at this surface. So this is called, sometimes called the no boundary proposal, because it has only one boundary and no boundary in the past. You sum over all closed Euclidean geometries that has this surface with the given fluctuations that you put there. So this path integral will give you the ground state of these fluctuations. Now, given you have these this ground state wave functional, it's also called the Hartle-Hawking wave functional. This was proposed by Hartle-Hawking. And so given such a wave functional, you can evaluate 2-point function, 3-point function, and so on. So that's the idea. And basically, and one more thing is that nobody does these wave path integrals in full glory. People usually make approximations like saddle point approximation and so on. Now this is one way to get a wave functional, that is you do a path integral. Now another way to get these wave functionals is to solve what are called Wheeler-DeWitt equations. So these are like some functional differential equations that you impose on this allowed wave functions of the theory. So this is a bit like in electromagnetism, if you have no charge, then del dot E is equal to 0 in a given slice. So you, even when you put some electric field on a slice and evolve it, you can't put any arbitrary electric field. It has to satisfy this condition, del dot E equal to 0. So this is a bit like that in the context of gravity. So if you solve this, so this is done by Subrat Tunir, Priyadarshi and so on. And so you will get a set of allowed wave functionals. So now what you have in your hand is some wave functionals other than Hartle-Hawking wave functional. And people have been computing correlators in Hartle-Hawking wave functional. Now what we would like to do is that computing cosmological correlators in these new wave functionals, and to see whether there are some interesting results. So the work is going on. I won't go into technical details, but roughly one example I can give you is that let's say your Hartle-Hawking ground state was a Gaussian state, just free theory, then the 4-point function will be product of 2-point functions. Now, when you, in these new states, excited states on top of this Hartle-Hawking vacuum, when you compute a 4-point function, it will be non-trivial. It won't be just 2-point function times 2-point function. So structurally, there are some differences, but we are still probing into how it can be related to observations and so on. Right now, we are just computing these correlators. And yeah, I will just summarize. So our universe had inhomogeneities, anisotropies that are correlators. And these can be related to correlators predicted by a theory of inflation. And wave functional method is one method to do that, to perform the computation. And till now, huge amount of work has gone into cosmological correlators in Hartle-Hawking state. And like people have found new geometry, positive geometry, some aspects are coming out, but there are states other than Hartle-Hawking state. And it would be interesting to understand correlators in these states. So thank you. Thank you.
Thank you, Ashik. Do you have any questions?
Thanks for the talk. So I was wondering, so since you mentioned that in the micro, let's say hundreds of microkelvin scale, you should be able to probe it. So is this delta phi, the fluctuations, is it the dominant factor in the microkelvin scale, or is it still suppressed by some other?
These are quantum mechanical fluctuations, delta phi. These are really small. But the idea is that these can be related to the classical fluctuations you see today. The classical fluctuations which we see today, like you mentioned, hundreds of microkelvins, these can be observed, but the earlier ones are not like microkelvin order and so on. These are like really small quantum mechanical fluctuations.
So what is the scale there?
Scale there? Oh, this I don't know. Maybe inflation is happening around some 10 to the power 16 GeV and so on, but fluctuations, do you have any idea? I don't know actually.
You said that you are finding these states by solving Wheeler-Dewitt equation, right?
Yeah.
I thought that Wheeler-Dewitt equation has some operator ordering ambiguity, and like how are you dealing with those, or do you face those ambiguities?
Yeah. Okay. So there are some ambiguities, but I think just like normal ordering prescription that we give, we can get around this. Maybe Priyadarshi and Tunir can get it.
It was in the leading order. In the leading order, the normal ordering did not matter. Okay. But if you go to subleading order, I think it will matter. Leading order in omega, like in the late volume.
Same result, or are we trying to find out the correct wave functional? Is that the...
Yeah, actually, like the result observationally, we have only seen this 2-point delta phi correlations. The results of that, like even that 2-point graviton thing, we haven't found. And observationally, like only this 2-point function people have seen. But if you want to distinguish between different theories of inflation and so on, you should actually look for 3-point correlations, and which I don't think people have seen.
Thank you, Ashik, for that talk.
Thanks.